Welcome, ladies and gentlemen. Let's go ahead and take a look at our function behavior Bellwork. So our goal here is to analytically sketch a graph using our knowledge of the relationship between original function f, its first derivative f prime, and its second derivative f double prime. So let's go ahead and take a look. We want intervals of increasing versus decreasing behavior. Which derivative is that? Increasing versus decreasing behavior, Riley?
The first derivative.
First derivative is good, and then concavity, right? Concavity, which derivative is that? Sophia? Second derivative, and so let's go ahead and we'll go in order here. We'll get our first derivative. Go ahead and share with the class what f prime is based on my definition f. Brendan?
Negative 4 plus 15.
Awesome, thank you. We know the only place that f can change behavior, that is switch from increasing to decreasing or vice versa, is when we have a critical value. And f has a critical value when f prime is undefined or when f prime equals 0. And as I survey my f prime function, polynomial, no values of x are going to make this undefined. So all I need to do is to consider when this equal question mark 0. So I'll go ahead and fully factored form and then set each individual factor equal to 0 and solve since we're dealing with polynomials. So I'm going to grab in here and maybe grab a negative 15x squared just to make my leading coefficient and the remaining factored form positive. So x to the fourth. Sorry, so x squared would be x squared times x squared is x to the fourth. And then minus 1 equals 0. How's that? How do you do with the factorization? Sydney?
Question.
Yes.
So is it always good to pull out that negative, or is it bad to leave them there, or?
It's not bad, no. It makes it easier for me to factor this because I like having a positive leading coefficient if I'm going to be doing any factoring and stuff like that. But it's not bad. It's up to you and it's personal preference. So why not? Let's go fully factored form all the way. It looks to me like x plus 1, x minus 1. So we have critical values at x equals 0, x equals negative 1, x equals positive 1 at this time. Go ahead and check out your paper. Raise your hand if you had all three critical values, 0, negative 1, and 1. Great. What does that do for us? It allows us to perform a sign test on my first derivative, f prime, number line, and that will determine then the behavior of f increasing versus decreasing. So I'm going to try to switch that on this page. Yep, we can do that on this page. So we'll go ahead and do my f prime number line. Make sure we label it as such. On that number line, I'm going to put the critical values, negative 1, 0, 1. And now I'll perform a sign test by choosing x values on each subinterval. And I'm going to plug them into my fully factored form because it's easy for me to see the sign overall of f prime by using the fully factored form. So what's a convenient x value to the left of negative 1? Danny?
Negative 2.
Negative 2, let's do it. Negative, x squared is always positive, so negative times negative times negative. Gosh darn it, I'm getting overall odd number of negatives multiplied together. Negative, yes? Convenient x value in the next subinterval. Grace? Yeah, let's do negative 1/2. So negative, always positive. So negative times positive times negative. Two negatives multiplied together, I'm getting a positive. Convenient x value on the next subinterval. Sydney?
1/2.
1/2, I'm down. Negative, positive, negative. So positive again. Interesting. And a convenient x value to the right of 1, Vivian? 2. Thank you. Negative, positive, positive. Overall an odd number of negatives, so negative. Take a look at your f prime number line and raise your hand if we match. So did you get the same f prime? Hey, that's good. Okay, so we're gonna have to figure out what's going on here because we had a critical value at x equals 0 and a horizontal tangent, and yet we didn't change behavior. So we'll see how that shakes out. Next up, f double prime will tell us about my intervals of concavity. Concave up, we know is a right side up bowl shape versus concave down can be described as an upside down bowl shape. And so I'm going to go ahead and get f double prime involved. Brendan has already graciously told us f prime, negative 15. And negative 15x to the fourth plus 15x squared. Now I'm going to call you for f double prime, Tyler.
Okay.
Ooh, waka laka mahiki. Sorry, so sorry. Circus time. My bad.
Negative 60x to the third plus 30x.
Plus 30x. Awesome. Thank you, Emily and Tyler. Got your back. For reals, y'all. All right, so what do we need now? We need our potential point of inflection x values, right? And where do we get those? Kind of the same thing we did with f prime to determine the critical values of f. Our x values from potential points of inflection come from when f double prime is undefined or equal to 0. Polynomial again, so no places where f double prime is undefined, but it could equal 0, question mark. So I'll go ahead and do fully factored form again. It looks like we can grab out a negative 30x. I'm going to do it just so I can make a positive leading coefficient, optional. And positive 2x squared
Plus 1.
plus 1 minus 1. Minus 1?
Minus
She. Right. Great. So are there any places where this, right, where this equals 0? Well, certainly. It looks like, again, critical value x equals 0. But here, we can go ahead and find additional critical, I'm sorry, not critical values, rather, but possible point of inflection x coordinates by setting this equal to 0 and solving. Does x squared ever equal, does x squared ever equal 1/2? Certainly. When x equals plus or minus square root of 1/2, and that's two different x coordinates. X is given by the positive and negative, what, root 2 over 2? And why am I changing that all the way to root 2 over 2, which you don't have to do either? But just because I know, again, for my unit circle, that's like 0.7. So it might help with my sign test. Okay, it might help with my sign test. All right, so what do we need now? We need f double prime. Da, 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 da. So we got my f double prime number line. And I'm going to get a little bit longer here because we've got some work to do. So we need 3 possible point of inflection x coordinates. Possible point of inflection x coordinates at x equals plus or minus. I don't even know what to do. What we're going to do with that. Let's just start over. Root 2 over 2 and 0. All right. So that's what's going to go on our list. So negative root 2 over 2, 0, root 2 over 2. Okay. Before we go any further, I got to stop and check and see how many got this for your critical value. Possible point of inflection x values. That's good. Okay, that's good. Now the tricky part. How are we going to do a sign test with these nasty values here? Well, remember, while the critical or the potential point of inflection x coordinates might not be very pretty, we have our say in what we want to choose for on each subinterval. That's up to us, and let's try to make our lives easy. And so if we want to the left of negative root 2 over 2 to perform a sign test, let's choose something that makes it easy to do, right? This is about negative 0.7. So how about negative 1? Let's do negative 1. I can do negative 1. So we'll go into f double prime fully factored form. Negative 1 in for x makes negative times negative is positive. Negative 1 in here makes this a positive 1. 2 minus 1 is still positive. So I've got negative times positive. Even number of negatives overall is positive. Is that what you guys got? Yes. Again, negative 0.7. So I'm going to choose negative 1/2. So negative 1/2. Negative times negative is positive. Negative 1/2 in here makes this 1/4. 2 times the fourth is a half, minus 1 is negative. And so I get negative times negative times negative. Overall, an odd number of negatives. All right. I'm getting negative there. Did you guys get that? Yes. Positive 1/2. Negative times positive overall is negative. Positive 1/2, 1/4, 2, half minus 1, negative. So I'm getting negative, positive, negative, an even number of negatives overall. Positive, and we'll go ahead and choose 1, negative, positive, overall negative. Raise your hand if you had this number line sign chart. You did. Hey, let's put it all together and see what we have. Wow. We need a little something or other in order to get my party started. So if we went ahead and did x, f of x, and put my critical values on here, maybe one on either side, we can get an idea of what this might look like, right? So we'll go ahead and put on our x coordinates of the critical values. We're 0, -1, 1. Our possible x coordinates of my points of inflection look like negative root 2 over 2, 0, and positive root 2 over 2. Let me put all those on there. So I've got -1, negative root 2 over 2, 0, root 2 over 2, and 1. And we might need one on either side. All right, let's do it. -1 on my original. -1 to the 5th is -1 times -3 is +3 minus 5 is -2. You guys get that? Yes. That is a local minimum. Local minimum. Okay, good. So we've got local min there. Negative root 2 over 2 is the x coordinate of a point of inflection. What's the corresponding y coordinate? Oh, do we have to? I'm gonna leave it in there. You know what I'm saying? I'm just gonna get a decimal approximation on my home screen. So what do we need? We need -3 root 2 over 2 to the 5th plus 5 root 2 over 2 cubed. We'll get a decimal approximation for that. 0, I got it. Same thing here. That's a negative. And same thing over here. But this time it's root 2 over 2 to the 5th plus cubed, and 1, -3 plus 5. Now I'm getting +2. Are you guys getting that? +2? Okay. Awesome. So I'm going to pull up the emulator here. And I know that you guys are already ready with your decimal approximations. Thanks for that. That's awfully sweet. On my home screen, pretty much love math. Love this class. So awesome. All right. So on my home screen, I'm just going to get a decimal approximation for that. So if I had negative root 2 over 2, right? If I had negative root 2 over 2, we know that's about negative 0.707. If I wanted to evaluate that, I could store alpha A quick and do -3 alpha A to the 5th plus 5 to the 5th, so darn pretty print, plus 5 alpha A cubed. Yes? 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 Also, I can get about negative 1.234, so that's about negative 1.234. And so is this going to be exactly the opposite sign? Right? Is that going to be about positive 1.24? All right. Let's see if we can't do it. I'm pretty excited about this. So we're going to do -1 comma -2. That's about -1. Okay. So for my scale, it looks to me like we could go and we want -1 comma -2. That is a local min. -0.7, -1.24. That is a point of inflection. 0, 0. that is neither a local min nor a local max, horizontal tangent, but point of inflection. Root 2 over 2, comma 1.24, about 0.7, 1.24, about. That is the point of inflection. 1, comma 2. Yes? And that is a local max. Gosh darn it, can we put it all together? So we've got rating, decreasing to a local max horizontal tangent, point of inflection. So I'm going to come down, switch level, switch. All right. Moment of truth. That's supposed to be changing concavity. Moment of truth. Let's go ahead and do a similar window. So what do we do? I went negative 2 1/4, 2 1/4. All right, so what do we want? We want negative 3x to the 5th plus 5x cubed. Oh, level, and oh my gosh. Are you even kidding me right now? That's so good. I mean, mine's not, but your guys' is really good. So that's awesome. Okay, so who had that shape? Did anybody get to the end result all the way? You did. That's great news, because this is exactly the kind of thing that you're going to have to do analytically on the non-calculator portion of our test. Everything's going to be great. So you have to be able to do something like this. Notice how our critical values and our possible point of inflection x coordinates weren't so pretty, and yet we could still do a sign test by choosing convenient values on each subinterval. Again, we're only concerned about the sign of the derivatives on each subinterval. It doesn't have to be exact evaluations, and that can help you save time and energy on the test. Okay, what questions do you guys have about our Bellwork? That was great. We're going to go ahead and, that's for you, Principal. Pause the recording and take care of our OTL number 2 check. Okay, ladies and gentlemen. So today we're going to expand our derivative applications to include optimization. We saw optimization last year. Of course, we're going to up the ante a little bit this year in BC, okay? And what allows us to utilize our analytic methods like we did in Bellwork in order to find maximums and minimums for these functions is really a special case of the mean value theorem. So what I want you to do is go ahead and take a look at this picture for Rolle's theorem, which is just a special case of the mean value theorem. If f is continuous on the interval a to b and differentiable on a to b, and here's the addition, f at a equals f at b, so we'll think about how that's going to influence my picture, then there exists an x equals c on a to b such that, oh my gosh, that sounds like gibberish. Well, let's go ahead and get a picture in here. I know I have an interval a to b. We also know that f at a equals f at b. And so I need to have function values, right? I need to have function values that are equal, that's y coordinates, at x equals a and x equals b. So I'm going to go ahead and do here, and I'm going to do here. And we'll pretend that now is f at a and f at b. Now I need continuous function on the interval a to b and differentiable. So I need smooth, well-behaved, no corners or kinks, no vertical tangents, no discontinuity. So I'll go ahead and do, does equal? Does anything look equal? Better? It's my heart, no? Ha! Good. So what can we conclude then about this x equals c value on my interior of the interval a to b? Well, somewhere, right, somewhere on that interval, I have to find an x value where what must be true? Can we say that all the way out? Can we say that all the way out? Danny?
The f prime of x has to equal 0.
F prime of, I'm going to go so far as to say C has to equal 0, absolutely. So the slope, right, of the secant line connecting those endpoints is 0. Then somewhere on that interval, the instantaneous rate of change, that is the slope of the tangent, has to be 0 as well. And we can find that x equals C value. In this case, it looks to be right about here. Yes? All right, so that's Rolle's theorem. And gosh darn it, I was going to get this on the printable, but then I would have kicked it to 5 sides. I mean, 4 sides. For the printable, it would take forever to copy those out. All right, so let's go ahead and take a look then at our maximal cylinder exploration, which is going to allow us to find optimal solutions. This will be a combination of analytic and calculator means. And so I want you to go to number 13 and switch the window for y. I copied my x window from the equation object in Word and forgot to change the upper y coordinate, and so it shouldn't be 4.25 again, the same as the x's. It should be 50 or so, right? And again, you can experiment with your own window too. So that was a typo. All right, so we've got stamp eligible items, and our stamp eligible items are 4, 9, and 15. So 4, 9, and 15 are stamp eligible items. I'll add that to our whiteboard. And we can go ahead and get started. I'll pause the recording and we'll come back together to solidify our findings. Okay, ladies and gentlemen, let's go ahead and take a look at the findings from our maximal cylinder exploration. Firstly, when looking for an optimal solution, typically we're talking about a global extreme as opposed to just a local extreme. We want to know the best possible configuration, right? So it could occur in a couple different places. Firstly, the maximum/minimum value of a function f must occur at either, right? Either, what? Can we fill this in? Can we fill this in without me saying? So what's one place, right? What's one place that the maximum value could occur? Sophia?
One of the actual domains.
Absolutely. So a maximum or minimum value, an extreme, could occur at one of the endpoints. Good, thank you. And where else could the extreme occur, Riley?
At a critical value.
At a critical value, good. Great. So the maximum/minimum value of a function must occur at a critical value or at an endpoint, okay? Or at an endpoint. And so that narrows down our search because now we only have to check a couple different places. All right, so we've got an optimization strategy that I made up. I didn't get this from a book. I made it up just as a kind of a strategy. I don't want you to think it's a sequential list of steps that'll work every time. It's more of a strategy that hopefully will empower you with a process that you can use to help you figure out what the optimal solution is in a given problem. So we're going to read the problem carefully, write down the quantity that we're trying to optimize. You know from last year, right, you got points actually just for writing down what it is that you're trying to do. That goal, right, provides focus for the rest of the problem. It tells you what formula you're going to write. You're going to rewrite that formula as a function of a single variable, right? That's what you're working with, and so it provides the focus for the rest of the problem. Drawing a picture and labeling with relevant quantities and variables will allow you to get the algebra into your formula and equations. You're going to write a formula for the quantity that you want to optimize. That's your goal from number 1. You'll use relationships in the problem that are given information to write the quantities formula as a function of one variable. Consider its domain. In this case with the cylinder, right, that was helpful because it narrowed down my search. Use the closed interval method / first derivative test or the second derivative test, which we'll look at again, to find the optimum result. And then we'll answer the question that was asked. Be sure to include unit. So what I did, this is not on your printable. I made you a copy of this. I didn't want to give it to you before the exploration because it's for exploration. Fat fingers, so it's tough. Okay. So let's go ahead and make sure that we are familiar with the tools in our bag, so to speak, comma baby. So the closed interval method. For our closed interval method, I wanted you in your exploration to get reminded about our main tools. The first of which is the closed interval method. We can evaluate the function at the critical values and at the endpoints, and then compare to find the optimal solution. Clearly, our 256 pi over 9 cubic units was better than the zero volume or the zero volume from our endpoints. And so we know that was going to be the optimal solution. So we can evaluate the function at the critical values and at the endpoints, compare, and then pick the best option. If we don't have a closed interval, right, and this was the last two questions, got you to think about different methods that we might use in different scenarios. If we don't have a closed interval, we can still perform the first derivative test, and that will allow us to determine the intervals of increasing versus decreasing behavior of my original, and still determine if we're talking about a maximum or a minimum at our critical values. So our first derivative test, we construct a y prime number line with the critical values and perform a sign test on each subinterval to determine the behavior of y. From that, we can ascertain where y has a maximum or minimum. And then another useful test that we didn't do much last year is the second derivative test. The second derivative test, if f prime of c equals 0, right? So think about what that means. If f prime of c equals 0, we're talking about a horizontal tangent. So that's a potential maximum or minimum, potential turning point. And f double prime of c is positive, then f would have a minimum at x equals c. What? Well, let's think about that. If we have a horizontal tangent on my function, a horizontal tangent, but we have concave up shape, then we must have a minimum value there at x equals c. Contrast that with f prime of c equaling 0. So now we've got a horizontal tangent, but f double prime at c was negative. What feature must we have at x equals c? Well, then we must have this kind of behavior. So we must have a maximum. You guys see the difference? How would that save us time? Well, instead of having to evaluate f prime twice, one on either side of a critical value, we could evaluate f double prime once. If it's positive, then I know I'm dealing with a minimum. If f double prime were negative, then I know I'd be dealing with a maximum at the place. The only thing is that you have to do a second derivative, right? And so they kind of even out, right? You still have to do second derivative and then eval, as opposed to evaluating your f prime on either side. All right, so that's for you in printable, which brings us to our strategy again. We're going to hold off on the can because it's a little bit more involved. We're going to save it for tomorrow. We'll do 2 days with optimization so you have an opportunity to practice in more detail. Next time, let's go ahead and close it up for the day then. I'd like you to briefly describe the closed interval method as a means for determining extrema. Be ready to share with the whole class. And when you don't have a closed interval, how can you still determine a function's extrema? So when you don't have a closed interval, how can you still determine a function's extrema? And be ready to share. Go ahead and share with the class a brief description of the closed interval method. So what's a brief description of the closed interval method? Marissa?
So you evaluate the function at critical values and the endpoints, and then you compare to see which ones is the maximum.
Absolutely. We can evaluate our function f at the critical values and at the endpoints and compare. We can select the optimal solution from those choices. So we'll evaluate my function f at the critical values and at the endpoints, and then we'll compare in order to pick the optimal solution. When you don't have a closed interval, how can you still determine a function's extrema? So when you don't have a closed interval, how can you still determine your function's extrema? Riley?
The first derivative test.
Yeah, we can utilize the first derivative test, which is a f prime number line and sign test to determine the increasing versus decreasing behavior of my original function f. Or now, this just in, what's our other one, right? What else could we do? Riley?
Take the first derivative and the second derivative. Or where the first derivative equals 0, take the second derivative, and if it's positive, it's sum in, if it's negative, it's max.
Yes! I'll just call that second derivative. Because I'm visions of carpal tunnel just thinking about getting all that down, so I'll call that the second derivative test. That's exactly right. And a wonderful explanation of the second derivative test. Thank you, Tyler. Yes! Gosh darn, we got it. And so guess what? Your assignment just got shorter. What? Your assignment just got shorter. We're going to hold off and do the CAM next time.
Are you kidding?
I'm serious.
Yay!
So we got 3. Next time you're gonna have more practice time, hopefully. So we've got 5, 7, 9 from page 231. Make sure that you're following the whole optimization strategy process so I can kind of see each step. Great work today, you guys, and I'll save the recording.